All right, recording is rolling. So it is Wednesday, October 26th. And well, first thing before we jump into the physics is there's an update for because of the Hurricane Days deal. Okay. So what is getting out of the email was that I don't think they're making us come to school any additional days. What they are doing is a couple things. One thing, and hopefully this is just a minor thing, is that they're changing the definition of when semester one ends and semester two starts. So the first few days of January, like January 6th, January 9th, they're adding to semester one, right? Hopefully that doesn't change things. Hopefully exams are still in December, but I don't know. We'll see. But I don't think that should really affect us. Hopefully not. Okay. But the other thing that will be more apparent and more immediate is they're lengthening some of these Fridays. So you guys know Fridays are always short days, but not these four anymore. So the first one come up is next Friday, not 2 days from now, but well, 9 days from now. So there you go. 9 days from now, Friday, we're gonna have a full day. All right, so physics. You guys remember this table we've been working on? Right, so we spent the last couple of days looking at this new way of thinking at physics, right? Which is that energy can take different forms. We've been specifically looking at these different mechanical forms so we can construct conservation of energy formulas and then solve problems. I'm going to do as many as I can today. I was originally planning to tell you guys about universal potential energy, escape speed, and all that, but we're gonna have to bump this probably to Monday because tomorrow I'm gonna have a lab for you guys. I'll spend a couple minutes of class setting that up for you guys, and then of course Friday's laptop day. So right. So it drives me crazy. I can't quite get to this, but we're gonna have to bump that a few days. All right, but we'll do as many as we can. All right. So we did the first two already, so you guys have an idea of what we're doing with this. Right. So let's keep it going. Okay. Now, I should tell you that all these examples are closed systems except for a couple of them, and they're right here. And they're the next two that are lined up. So these are going to be open systems. And all that means is that there's going to be an energy transfer into or out of the system, which all we have to do is tweak the formula a little bit. It'll be perfectly fine. Okay. So we have a kid sliding down a hill of length L, and there is friction. There is friction. Ooh, okay. So if that's true, what's in the system? Well, I care about the kid and the sled. Right, care about that. And so that's one object. Oh, guys, the fact that there's a height change, right, means I have to include the what? The Earth, right? The entire Earth, right? First two, there's a height change, okay? Because the Earth is pulling with some gravity force. The Earth is providing a force, right? If I don't include the Earth, that would be an external force. But if I include the Earth, I've internalized it to the system, right? You might include the surface. Here, I'm just going to look at this as my system. I'm going to define this as an open system. So what's the energy at point A? You guys see the fact that the kid and sled is elevated has what kind of energy? Yeah, potential energy, right? Gravitational potential. That's this right here. Right, so here's my shopping list right here. I'm just like, okay, we're going from boom to boom, pretty much, right? Okay. And then there's some work done by friction along the way. So boom, boom, boom. Okay. Let's put those pieces in play. So it starts off with all gravitational potential at the top of the hill, subscript A if you like. Right? By the time he gets to the bottom, do you think he's probably like speeding up as he's going down? Right? So he probably has some 1/2 mv squared at the end. Right? Now that's not the whole story because if it was, then this would be like an air pocket table. You just tip that up and that would explain the whole thing. But the fact that friction is pulling energy out of the system, I'm going to say minus force of friction times the length of the surface, because isn't that the distance? Force times distance. That fits this form right here. Okay. And I'm subtracting because it's taking energy out of the system. Right, so let's put this on paper. I'm going to say the sum of energy at point A equals the sum of I messed up already. All right. Energy at point B. Maybe I'll save this paper for one of the later examples. Oops. I was setting up a closed system. Start over. Okay. I want to say this. This is an open system. So we're looking at something like this. The sum of energy at point A minus the work done by friction equals the sum of energy at point B. Okay. Right. See if I left that off, that would be a closed system, but I've got an open system. Okay. So at point A, it's all gravitational potential energy. Okay. The work done by friction, of course, is the friction force times the length of the surface. Okay. And we'll be left over with some 1/2 mv squared at the bottom of the hill. Okay. Of course, he's at the bottom, his height goes to 0, so he only has kinetic, but no potential. Okay. Okay, is that okay? That's it? Okay. All right, now here's where we could go possibly a couple of ways with this. Like how we solved the first two, see how we solved them in terms of variables. Like we could just chug through some algebra and solve for VB as an expression of all this other stuff, right? I'm not going to do it with you guys. What I'm going to do is just make up some values for these, right? And then we'll just solve like in terms of numbers. Okay? So a little bit different from what we did. So let's give this kid sled a mass of 60 kilograms. Let's call the gravity of the planet 10 meters per second squared. Okay, let's call the height change like 5 meters. Let's have the length of the hill be like 13 meters. Just picking up numbers. Right. Now pause right here, because if you think back to geometry, if you know the height and you know the length, could you do like inverse sine of 5 over 13 is this angle to the horizontal, right? Which is like 22.6 degrees, right? We're not going to do anything with that. That's just a side thought, right? We could, right? But no, right. All right, let's go. What else should I do? Okay, friction force. Okay, let's go to the friction force. All right. Oh, I'm gonna call this. Don't want to get myself into trouble here. Let's go 100 newtons. How about that? 100 newtons of friction force. Right. Again, we could get a bit more into the weeds if you wanted to. You could say, well, the friction force is coefficient friction times the normal force. Normal force is mg cosine theta. Theta is based on this h and this L. Right. Let's just keep this kind of big picture. Right? We're gonna take these numbers. We're gonna feed them into this expression. We're gonna figure out how fast this kid's going to the bottom. Okay. Got that? Okay. All right. So let's just start popping in numbers. All right. So 60 kilograms. The kid in the sled. Right there. 10 meters per second squared. Right there. The height change of 5 meters. That's a vertical change. Right there. Let's suppose you ran the coefficient of friction times normal force, blah 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 blah, and it comes out to the value I gave you, 100 newtons. It's 100 newtons force for a distance, the full length of 13 meters. Right there. Okay. And that's going to give this kid in sled, which again, 60 kilograms. Some speed at the end. Right, and don't forget to square that. Right, this is going to end in a square root. You guys know the last step's going to be a square root, right? Right, good so far. You guys follow along? All right, so let's see. Right. One of the reasons I'm giving you guys numbers is so we can see how many joules, because we're doing energy accounting, right? So what is 60 by 10 by 5? Right, we're looking at like 3,000 joules of energy that this kid starts with, right? 3,000 joules at the top of the hill. Okay. But you know what? It looks like 1,300 joules have been subtracted because of friction. Okay. Now, that energy doesn't disappear from the universe. It transfers into probably thermal energy, maybe starts to like melt the snow, like heats up a little bit. Okay. But you guys see the difference? It's like, what is that? 1,700, I think, 1,700 joules difference. Right. That's all going to be routed into kinetic energy and give a speed. Half of 60 is 30. I'll just knock that out right now. Okay. VB squared. Right, second. Okay. All right, so we got 1,700 joules, which is this expression. Okay. So 30 kg VB squared is the remaining 1,700 joules. Okay. Is that okay? So I'm 2 steps away from getting the answer. Okay. Divide the 30 kilograms down. That's half of 60 kilograms. That's where it comes from. So it's 1,700 over 30. Right, that's 56.7. 56.7. Now joules divided by kilograms is meters squared per second squared. So when you take the square root, you get 7.53 meters per second. Just like that. Okay. I had 2 digits of significance. I could say this. Speed at point B is 7.5 meters per second. So you guys got that? So given those inputs, right? Questions so far? All right, so let's do the other open system question that I threw at you guys, which is a car brakes to stop. Okay. So I definitely care about the car. I'm focused on the car. Okay. You maybe can make a case for the Earth because there's a gravity force, which is causes a normal force, which allows for a friction force, which is important. I'm going to leave that off. The road definitely puts a force on the car, but I'm going to treat that as an external force. So I'm just going to have a system consisting of only the car, and there's an external force on the car. Okay. Okay. Right. So when this car is in motion, right, just before the guy hits the brakes, what kind of energy does the car have? Kinetic, isn't it all 1/2 mv squared? Is that true? Right, and that's whatever the initial velocity was. Then the guy slams the brakes and comes to a stop. Now, when he comes to a stop, does he have any kinetic? No. Has he rolled up any hills to come to a stop to get potential energy? No. Right? You guys know the overpass over I-95. If you're like rolling up that hill, it slows down your car in a hurry. I bet that's because some kinetic energy is transferred to potential. Now, that's one way to think of it. But we've got none of that either. There's no springs. What kind of mechanical energy does the car have at point B? Nothing. Zero joules. Right? And the only way to get there, again, because it's an open system, I'm going to say there is minus force of friction times the stopping distance along the way. Okay. Is that right? Okay. Now, let's go ahead and finish this railroad pass, and there's a lot more I want to say about this problem, because this is a really classic physics scenario. Okay. But I bet a lot of you guys are looking at this last quadrant and say, I know what goes in the cell. Right? Because guys, what's the speed of the car right at the end? 0, right? Isn't it just 0 meters per second? Right. I mean, I have kind of a generic question for all these questions, but you could ask different questions about the scenario. And that's where I want to switch gears a bit. I'm going to just flash some notes up here that I showed to my AP class. Oh, whoops, sorry, that's here. This one right here. Okay. So this we put together in AP, but I want you guys to be able to read the music of the solution in terms of variables and say, like, what other questions could be asked? What would the solutions be? Right. Now, quick reminder. You guys remember free body diagram for the car? If it's moving to the right and it's braking to a stop, okay, weight, normal force, which is equivalent to the weight, friction force. You guys remember all that? Okay. Here's friction force, coefficient friction times normal force, substitute in, blah, blah, blah. So something like that. Right. I'll let know, right? Okay. So then you could come up with this expression. That's what we just did, right? Kinetic energy minus work done by friction, force times distance goes to 0 joules, right? And then you could like solve for stuff. So here, I did a bunch of substitutions. Friction force is coefficient friction times normal force is equivalent to the weight, right? And then suppose you wanted to solve for the braking distance. You just do a little bit of algebra and you're going to get this expression right here, right? Here's the braking distance. It's a function of how fast was the car going, the coefficient of friction between the tires and the road, and the gravity of the planet, okay? I have a couple of questions that, again, are not on that table because the table question is what's the final speed, but that's obviously 0. But I got my own questions. Here's the first question. Suppose you have kind of a small car and kind of a big car. You guys see 1,000 grams is twice the mass of 500 grams. Right? So you got a small car and a big car. Right? Let's say these cars are on the same road. They have the same tires, therefore same coefficient of friction. They're on the same planet. And let's say they're moving the same speed, side by side. And they slam on the brakes at the same time. Brake to a stop. Okay. One of 3 things is going to happen. Right? And I'm about to see show of hands. I want to see if you guys can figure this out based on the solution right here. All right. Possibility 1. Maybe the small car is and brakes to a further distance. Possibility 2. Maybe the large car takes the longer distance to brake. Possibility 3. Maybe they brake to stop in the same distance. Now, let me see what you guys are thinking. So show of hands. How many guys think that the small car takes more road to brake to stop? Who thinks that? Nobody say that? Nobody? Okay. Possibility 2. Who thinks the large car it's going to take more road to brake to a stop? Who says large car? Okay, so we got some votes there. Got some votes on the large car. Okay. Who thinks that these cars same braking distance? Oh, and that's getting some votes too, right? Actually, let's get more votes, which is a good story. That means you guys figured this out, right? Because the solution's right here. Here's your braking distance, right? How did you know that the different masses will brake at the same distance? Yeah.
More mass requires more to slow down, but also has a higher gravity effect, which means that there's more friction, so it cancels out.
There you go. Right. So you guys heard Caleb. He was saying, well, yeah, more mass means more inertia, which would tend to, you would think, larger braking distance, but that also means more weight, which means more normal force, which means more friction force. If you to double the friction force for double the mass. Right, exactly. Those 2 cancel out. So this is math independent. That's a really classic physics question. What I just asked you guys. If you guys take physics in college, like almost guaranteed you're going to get that question at some point. It might be a test question. Okay? And the answer is always, well, this is mass independent. Okay, it doesn't matter the mass of the car. Okay? Let me ask you guys a different question. Suppose you got two cars, okay? Okay. And they're identical in every way, right? But one car is going faster than the other one. Right now, and they slam on the brakes at the same time. So, right now, obviously, the faster one's going to take more road to brake to stop. That would be true, right? Right. But let's think about proportionally what that would be. Suppose one car was traveling at twice the speed of another car, twice the speed, to like 20 miles an hour and then 40 miles an hour. Okay. How much more road, like proportionally, like as a factor, like how much more road does the big car, or sorry, the fast car need compared to the slow car? Twice as fast. Is if you double that speed v, what's the factor of 2 squared? Is that 4? Does that mean 4 times the road? Yeah, for the same coefficient of friction, same gravity. Yeah, it's 4 times the road. What if you did triple the speed, like 20 miles an hour compared to 60 miles an hour? If you triple the speed, what happens to the amount of braking distance? 9 times? A factor of 3 squared is 9? Whoa, right? You guys said that's another classic physics question. So you could totally get that in college one day. Right? Or I don't know, maybe one of these quizzes coming up. It's not right your quiz, so might show up. A good quiz question. All right, moving. Oh, I like this next one, right? Because this one involves multiple types of multiple forms of. Well, again, here's our shopping list, right? So we're gonna get several of these. And so I got a block smashed against the spring, a lot like right here. I can smash this spring right here, and then pow, it's gonna release it. Pow, pow, right? And this block goes around this loop, and then it's off. And see if it gets to this point, it must be in motion and with some speed v, right? And I know that because there's a frictionless track, so to get around this loop, it better be moving some speed, right? And so what's in my system? I'm thinking of three things I have to have in my system. What's one thing? How about the block? And what else? What else? The were you guys saying the spring? Right. Okay. Because right at the beginning, all the energy is in the spring, isn't it? If you like compress it, right? And one more thing I have to have, the fact that there's a height change means you have to include the Earth. Yeah. Right, because Earth is it's going against Earth's gravity. Right. Now, some of you guys might think, well, hold on, should you include the track? Right? Because isn't there a force from the track? And isn't the track like changing the direction of the block? Right. Here's why I did not include the track. Right? Because the force from the track is a normal force. It's always a normal force. Doesn't normal mean perpendicular? Right. But the motion of the block is always parallel to the track. So the force from the track, normal force, and the motion of the block, like its speed, its velocity, right? Those are always perpendicular. You guys remember if you carry a textbook across the room, the upward applied force and the horizontal motion have nothing to do with each other, right? So that force doesn't do any work. Same story here. The normal force does not do any work on the block. That's why I'm not including the track in the system. Right? Also, the fact that it's just frictionless. See if there was friction, then maybe the track would matter. Okay. Okay. So energy at point A, guys. Where's all the energy? Right here. It's all in the spring, isn't it? 1/2 kx squared. Isn't that true? Right. But by the time it gets over here, right, well, the energy's gone. Part of the energy went into lifting the block, didn't it? So don't I have some of this kind of energy? Okay. Gravitational potential had to lift it. So that's where some of the energy went. And the rest of it, whatever's left over, goes into the what? Like the kinetic energy? Sorry, 1/2 mv squared, I meant to say. 1/2 mv squared. Again, at point B, 1/2 mv squared, right? Okay. Right. All right, so let's do same thing we did for last couple, which is give you guys some numbers. So let's go with a gravity field of 10 meters per second squared. Let's go with the spring constant of like 1,000 Newton per meter. All right. Let's go with a compression distance x. X is like the compression, how much you compress the spring, right? Let's go 10 centimeters, and I could call it like 0.10 meters. Isn't that 10 centimeters, 0.10 meters? Right. Let me do a quick calculation off screen here. Divided by okay. 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 Let's go. Let's give the mass of the block like 1 kilogram, 1.0 kilogram. Okay. let's say the height that it goes to is like, how about 40 centimeters? And I could call it like 0.40 meters. Is that okay? Okay, 40 centimeters is 0.40 meters, isn't it? Okay. If I said 40 centimeters, you wouldn't want to write down the number 40 because when we did calculations, everything better be in base SI units to get like joules and that sort of thing. Okay, so I think these numbers should work out. Okay, let's try this out. And of course, we're looking for speed at point B is something. Okay, this kind of goes in the next box a little bit. Next box is gonna be pretty simple. Okay, speed at point B is some number of meters per second we're solving for. Okay, we're gonna solve for this. How many meters per second at point B? It's gonna be the answer. Okay, all right, so doing some that's what I got this for. Okay, closed system. I got this set up. Okay. And at point A, it's all in the spring. That's 1/2 kx squared. And at point B, it's been lifted against gravity. Plus, it's going to have some kinetic energy left over. Therefore, we can solve for the speed at point B. Okay. So let's pop in these numbers. I got 1,000 Newton per meter. It's been compressed. Now 10 centimeters is 0.10 meters. That's being squared. The mass of the block, we're just calling 1 kilogram. Let's go gravity, 10 meters per second squared. Let's say the height from here to here is like 40 centimeters. That's 0.40 meters. And then 1/2, 1 kilogram. And then what's the speed at that point? Okay. All right, so energy accounting. Let's figure out how many joules is this? What's 1/2 times 1,000 times 0.1 squared? That's like 5 joules. All right, so we got like 5 joules of energy to start with. 5 joules. Okay, where's that energy going? Well, it looks like this right here is that 4 joules? Yeah, that is 4 joules. It's 4 joules right there. Okay. So we're going to have 1 joule of energy left over to go into its kinetic energy. Okay, 1/2. Well, it's like 1/2 of 1 kilogram. Okay. BV squared. Right? Is that true? Okay. Subtract this over. There's only 1 joule of energy left over. This is equal to 1 joule. 1 joule. Okay. So we're going 1/2 times 1 kilogram times whatever the speed is that we're solving for squared is 1 joule. Right? Start with 5, 4 went here, 1 must go there. Okay, multiply by 2, divide by kilograms, and then take the square root. So the speed at point B is the square root of, okay, so we got 2 joules per kilogram is meters per second squared. Okay, so the speed at point B is 1.4 meters per second. There you go. That's the answer. Go up here. 1.4 meters per second. You guys got that? That check out? And so energy counting. Okay. Any questions? Okay, you guys ready for next one? All right, next one. Oh, we got a bungee jumper. Bungee jumper dives off a platform and barely touches the ground before the cord retracts. You guys know bungee jumping, right? So you jump off, you've got this like elastic type rope. You'll be falling for a while, and then at some point the rope maximizes and it starts to stretch. Okay. Let's say this guy's falling, slowing down, right? And then it's about to hit the sidewalk, but it's like, oh, yeah, it's fine, right? And it's like slows down to stop right there, and then it's like reach down, like point, touches the ground, and then the cord retracts and shoot, he's back up. Okay. So I care about the jumper, right? The guy jumping. Okay. I have to include 2 other things in the system. What else do I have to include? Yeah, the earth, right? Because the fact that there's a height change, right? Isn't the earth like pulling down in the sky, right? And also, it's when it gets to point B, do you think that cord stretching, like the energy sort of gone into the cord the same way that when I stretch the spring, there's like spring potential energy right here? Hey, this is kind of like a bungee cord, isn't it? It's kind of, this could be like your bungee cord, right? We're going to treat the bungee cord like a spring. That's what we're going to do. Right? So I care about the bungee cord. Okay. Right, so at point A, what kind of energy? Potential energy, gravitational potential, MGH. Subscript. Okay. By the time he gets to point B, again, he's like slowing down and then like turns around at point B, doesn't he? Okay. Where has all the energy gone? Into the bungee cord. Okay. I could call that like 1/2 kx squared, where x is the amount that the bungee cord is stretched beyond its usual length. Right? Is that true? Okay. You guys got that? Okay. That could be the entire setup. Tell you what though, you guys see back in the setup, it says a jumper dives off the platform. If you want to make this a little bit more involved, you could say instead of like stepping off, you could like do a running jump, like oh yo, right, and like jump off the edge. And if he does that, then I could say plus 1/2 mv squared. Right? But whether you assume that or not, the fact that he's like just barely touching the ground, turning around at point B means his speed is what at point B? 0. Right. So yeah, this particular question, okay, the answer is just going to be 0. Okay. But you could say this plus this is equal to this, and then you could solve for other things, right? Like you could solve for like how fast could he run before, like if he runs too fast, then maybe this thing's going to stretch too much and it'll like smack into the sidewalk. Right? Or you could solve for like how high could he go up to and jump? What's the maximum stretch amount? What was the K value have to be for the bungee cord? Right? What could his mass possibly be? Because that's not going to cancel out, right? So there you go. You could solve for different things. Right, next couple of questions. Look, Atwoods. Got a modified Atwood. We got the classic double elevator Atwood. You guys remember these Atwoods? Right? Right. So now we have a new way of approaching these things though. Right? So after this block has moved so far, how fast is it going? Okay. Now you have a way to solve for this already. Okay. And one of these I'm going to take and solve it the old way, but then we've got a new way, this conservation of energy framework, right? And I'll show you that they're the same thing. So let's go ahead. Okay. I care about each mass 1, mass 2, okay? And I care about the Earth because again, there's a height change, so Earth's gravity is pulling for some distance, force times distance. Okay. Right, so there's my system, my closed system. Okay. Energy at point A. Do you guys see that M2 can fall? The fact that M2 can fall, it has some distance to fall. I'm gonna say that has some potential energy. M2GH. Oh, let's limit my picture. See that picture I put X. Can you guys write over X? Just call it H. Is that okay? Like some height change. You guys do that, right? Right. And that's all. That's the source of energy. The fact that this tiny block can fall down. Okay. By the time you get to point B, let's say point B is like right near the floor, so it's lost all its potential energy. But isn't it moving really fast? And isn't it also tugging along M1 with it? So would those each have a kinetic energy? I say 1/2 m1v squared plus 1/2 m2v squared. Right? It's not like a combination. Right? And like we're solving for this v. That's the speed of point B, isn't it? Okay. So you guys see our setup? Oh, okay. All right. Yeah, thank you. I got it right. All right. You guys see that setup? Okay. Now I do need to give you guys some numbers. So let's do this. Let's go. I'm going to call mass 1 3 kilograms, mass 2 7 kilograms, and let's call gravity 10 meters per second squared. And I'll call the height change like 3 meters. I know that's a big distance. That's like the height of this room, but we have integer values to work with. Okay, okay. You guys get that? Okay, so the question is, what is the speed at point B, like after falling 3 meters? Of course, they have the same speed, so it's not that. So closed system, the sum of energy initial is equal to the sum of energy final. Okay. And at the top, it's all gravitational potential energy for block 2. Right? And at the bottom, well, there's no more potential energy, but there's kinetic energy. I got some 1/2 mv squared for block 1, and some 1/2 mv squared for block 2. Right? And it's the same v. I could do v sub b, but it's the same v. You guys got that? Okay. Now, before I plug these numbers in and start chugging, let me share one other little detail here that you might be wondering about. Okay. Basically, M1 is like elevated at a huge height. how many of you guys are thinking, well, hold on, doesn't M1 also have a potential energy? Okay, now you could say that M1G times the height of this table, whatever. Okay. But the fact that M1 only ever moves horizontally, it had the exact same potential energy over here, so it just cancels out anyway. Okay. Also, the fact that it doesn't change height at all, I just ignored it. Right, so I don't have to write it. All right. So let's plug these numbers in. M2 was 7 kilograms. The gravity field was 10 meters per second squared. So the height change is 3 meters. And so that's the starting energy. Sometimes 3 is 21 times 10. It looks like 210 joules, doesn't it? Okay. So you guys see we have 210 joules to play with. Okay. Right, let's see where that energy goes. Okay. Well, got 1/2 times M1 was 3 kg times whatever speed it's going squared plus 1/2 times 7 kg times the same speed being squared. Okay. Oh, now I do know that this all has to total to 210 joules. Right? Do you guys think I can like factor out the v squared? Is that okay? Okay. And then I got 1/2 of 3 plus 1/2 of 7. I think it works out to be like 5. Okay. So I got 210 joules is equal to like 5 kg v squared is how it work out the math. Okay. So I'm going to divide this 5 over, but 210 on 5. It's like
Would you do the half or no?
I took care of that already. Yeah. Because 7 and 3 is 10, and half
Oh.
that. Okay, yeah. Right, so then v squared is 42. Now joules per kilogram is like meters squared per second squared. Okay. The last step is to take the square root. So what's the square root of all that? I'm looking at the speed at point B is 6.48 meters per second. So you can see about 6.5 meters per second, somewhere there, right? Second. So that's the answer. 6.48 or 6.5 meters per second. That's the answer. All right. You guys ready for the classic double elevator? Okay, this one I'll do 2 ways. So let's do the conservation of energy way first, and then I'll show you guys it's the same as the old way of doing it. Okay. Right, so I still got M1, M2, and the Earth. Okay, it's gonna be a pretty similar setup to what we did before, but a little bit different. Okay. So M2 falling still provides the potential energy. So M2GH, so it has potential energy and it provides the energy of the system. Okay. But this time the energy is going to go to 3 places. Right? Not only is each block going to have a kinetic energy, so 1/2 M1V squared plus 1/2 M2V squared. Again, it's the same V, they're tied together by string. Okay. But also, isn't it lifting M1 at the same time? M1GH and then plus all this stuff. Isn't that true? Okay. So not only does M2 fall, but it has to lift M1 at the same time. Right. So some of the energy goes there. Let's use the same blocks that we did before. It's like all these values from before. Let's just copy paste those right there. You guys see that? Okay. So same inputs. Right. I'll have this expression. So sum of energy initial equals sum of energy final. Okay. It's all being supplied by M2GH. Right. That's like the supply of energy. Like the demand for energy as well. These 3 bits right here. So it goes to lifting M1 and also giving each block a speed after that height change. Right. And we're solving for the speed. Is that true? Guys good? All right, so let's pop these numbers in. So I got 7 kilograms on M2, 7 kg. I got 10 meters per second squared. We're looking at a 3 meter height change. It's a giant Atwood, nice integer. Okay. Mass 1 was 3 kilograms. It's being lifted against gravity, 10 meters per second squared. We pulled up the same 3 meters. And then 1/2 got 3 kg V squared plus 1/2 7 kg V squared. Alright, just like that. Alright. Switch out the headset. You better luck here. All right, so hey, we have 210 joules to work with, just like the last question, don't we? 210 joules. Okay. But this time, some of those joules are going to lifting the small block, right, which didn't happen before. Okay, so it's not, it looks like 90 joules. What's that? Right, 90 joules going to lifting the small block. Okay, and whatever's left, what is 210 minus 90? That's like 120. The other 120 joules have to go into giving these blocks of speed. Okay. Oh, so plus, just sort of I did before. So that 3 and 7 is 10. Half that is like 5. Okay, got kilograms going around, and then v squared. Okay, sorry. Okay, subtract this over. Okay, so 5 kg times the v squared. Well, I've got 120 joules to work with. That's true. Okay, divide by 5. That's 120 on 5. That's 24. So v squared is 24. Now joules per kilogram is the same thing as meters squared per second squared. So I take the square root. And I'm getting the speed at the bottom is 4.90 meters per second. Just like that. Is that right? Okay. So again, same blocks as the last question, but now the double elevator arrangement. The speed at the bottom comes out to 4.90 meters per second. Hey, let's do a quick comparison here. These two problems, because it's the same blocks, just arranged differently, right? You guys see the single elevator actually moves faster after that height change, but the double elevator, the fact that some of the energy was diverted into lifting the block, overall they're going slower. Okay, that makes sense why that would be, right? Okay, now let me do what I promised you guys, which is do this the other way. Okay. The old way of doing it, remember, is that we solve for the acceleration first. And then if you know either how much time or the distance that this thing's moved, you could afterwards solve for, go kick back to kinematic motion and solve for the speed afterwards. Okay. But you know the answer should be 4.9 meters per second. Let's see if it works that way. So we're going back a few weeks now. So first, the acceleration of the system is net force over total mass. Okay. This is not conservation of energy. So I'm going back a few weeks now. Okay. Hey, net force, is that like, if these are 7 and 3 kilograms, is that like, do they weigh 70 and 30 newtons? Okay. So could that be, and they're playing tug of war with each other, tug of war. So I think that's 70 newtons minus 30 newtons. That difference is like the net force driving a total mass of 7 kg plus 3 kg. You guys remember doing this, right? You guys did a whole lab on this. You guys figured this out. So I have 40 newtons acting on 10 kilograms. So that's going to give me 4 meters per second squared. Okay. 4 meters per second squared. Okay. Once we have that, we can kick over to kinematic motion to figure out velocity, like speed. Okay. So here's your kinematic equations. Right? We've got these 3 amigos, but the top 2 involve time. Now, notice that I never mentioned how much time it's falling for, although you could solve for that. Okay. Actually, this entire packet, I've never mentioned time, have I? Right? The entire conservation of energy. Right? But we do know a distance change, so I definitely want to shop this third kinematic formula, right? Because we know it starts from rest, so v naught 0. Right, we're solving for speed. We're solving for this guy. Right, we know the height change. That's what x is, height change. Hey, and we just figured out the acceleration. We just figured out it's 4 meters per second squared given these particular blocks. So let's pop that in. So this is like step 1, dynamics. We're going to do step 2, kinematics right here, and say final velocity squared equals initial velocity squared plus 2ax. Where the x is, that's really the height change. This initial velocity just goes to 0. So the speed of point B squared is 2 times, and this 4 meters per second feeds in right there. Sorry, 4 meters per second squared. Okay. And the height change, remember, was 3 meters. I just made something up, call it 3 meters. So let's see, got 8 times 2 is 24. right? So square root of 24, whatever the square root of 24 is, right? Oh, square root of 24. That's 4.9. That'd be meters per second. Hey, that's the same thing we got using the energy method, right? It's the same thing, right? Right, but this is like a two-step process, point, point. First, this was just one step in some algebra. Right? Guys, that's the same answer. You guys get that? So dynamics, kinematics, 4.9 meters per second. Conservation of energy, 4.9 meters per second. All right, let's do this. We're gonna do one more from this packet, and then I'll set you guys up with your lab tomorrow. Give you guys some pointers going into tomorrow. Right. Again, like I really wanted to get to this last one so I could tell you guys about escape speed. We're gonna have to save that for Monday. Right. Tomorrow's a lab. Friday's laptop day. Okay. All right. So last one today. This one right here. I got a spring firing a ball vertically to its maximum height. And I can sort of simulate this right here because I kind of got these materials right here. Right. I got a spring. Instead of a block, I have an ink cartridge, right? So I can like compress this down, smash that spring. I did some work compressing the spring. Now all the energy's in the spring. I can aim it straight up and pow, right? And then fire this cartridge straight up, right? Ooh, interesting. That's maximum height because that seems like a special condition, right? Versus just some generic height. Right? What's in the closed system? Well, I definitely care about the ball, so I'm focused on the ball. But I should also include the what and the what.
Earth and the spring.
Boom and boom. The earth, there's a height change, okay? And also the spring, because there was a compressed spring where the initial energy was. Okay? So the energy at point A, you guys are going to write what? 1/2 kx squared, or k is the spring compression of the spring, and x is how, k is the spring stiffness, right? And then x is how much it's been compressed. So that's all the energy because it's at ground level. Okay? What's the energy at point B? What type of energy? Well, it has a height now, right? So could that be gravitational potential? MGH? Right? And the fact that it says maximum height means, ooh, it's not moving, is it? So is there any kinetic energy? No, that's the entire setup. Right? Now, if I said some generic height, you might want to add in plus 1/2 mv squared, but maximum height? No, that's it. So isn't this just equal to this, right? And then you could solve for stuff. So for example, suppose, here, give you guys an example. Suppose I do this experiment right here, right? I got a cartridge. What do I know the mass of this? Like so many grams, okay? And I smash it into the spring. It smashes down about a centimeter. I call it about a centimeter, right? So I know X is like centimeter. I know the mass of this cartridge in grams. I know the gravity field of the planet. And I fire this thing and it goes to some height. Suppose it goes like a couple of meters. Okay. Could I pop in a bunch of numbers and then solve for the K? How stiff is the spring right here? Right? I bet I could do that. Right? That's something you could solve for. Right? But that doesn't happen to be the question that I asked in this packet. This packet asks, what is the speed of point B? And what's just the answer to that question? Yeah, 0. Right? 0 meters per second. Okay. You guys get that? You guys get? Okay. Although could ask other questions. All right, so let's put a pause on this packet then. And I'll show you guys what you're doing tomorrow. So here, save that for Monday. Okay, so got a few more I want to do with you guys. Okay, so let me switch my screen. You guys might see back in the lab area that pulley system set up. Right, it's been set up since the first day of school. Some of you guys may have played around with it when you guys were doing some of your labs. Right, here's an older version of it. That's my old classroom back at Titusville High School. Right, you guys see like some pulleys and some weights and some like gold string wrapped around. Right, now if you rig up this pulley system the right way, you can get what's called a mechanical advantage, and you can lift something very heavy with a very small input force. Right, here's kind of how this works. So if you look really close, do you see like 1, 2, 3, 4 strings sort of extending upward from this movable pulley, right? That's attached directly to the weights, right? Now, of course, it's only one string, but it's just round and round and around, right? But do you think that whatever weight this is effectively divvied into 4 parts, right? So if this weighs like 100 newtons, do you think it's like 25 newtons each? And do you think therefore the tension of the string that you're pulling with is only 25 newtons? So you only need 25 newtons of pulling force to lift 100 newtons of weight. So it's like you're 4 times as strong. That's called a mechanical advantage, a 4-to-1, a 4-to-1 mechanical advantage. Right, let's get a bit easier to see picture of this. Right. So here's an animation. I'm going to play this at the beginning of class tomorrow. I'll remind you guys what's going on. Right. But you guys see this animation. Right now, what do you think that her mechanical advantage is here? Right? So they're trying to lift this pail. This pail is too heavy, full of water. So they rig up a pulley system themselves. Right. What do you think she's amplified her strength by? How many times? 3. You guys see 3? Because look at that movable pulley. Notice that there are 2 fixed pulleys, but there's 1 movable pulley. And that movable pulley is sort of it's 3 ropes up for that 1 weight down. So if that bucket weighs 100 newtons, do you think it's like 33 newtons in each strand? And she's only pulling 33 newtons, right? So what's the connection to conservation of energy? Well, the connection is this. She has to pay for her increased strength by pulling lots and lots of rope. Like every 3 meters of rope that she pulls, the bucket only moves up 1 meter, right? So the bucket moves up very slowly. And if you take her input force times the length of rope she's pulled, hey, isn't that like force times distance? Like the work she's done lifting the bucket? And on the bucket, if you take a very large force times a very small distance it moves up, do you think that those are probably going to be an equivalent amount of work, like work input equals work output? That'd be true as long as it's 100% efficient. So tomorrow I'm going to have you guys use your hands, string, pulleys, also spring scales. I'm going to have you guys back with spring scales, right? And figuring out what is your mechanical advantage for different setups, what would it look like, and then what is the efficiency of the system. Oh yeah, go ahead. Oh no, those aren't due for like a week. Yeah, so we're going to do those as a class next week. So all right, I will see you guys then. See you guys tomorrow.